Hello everyone, welcome again to Probability and Statistics for Data Science. Today we're going to talk about a really important concept in probabilistic modeling, which is conditional probability. Our goal is to provide an intuitive definition of conditional probability and then build upon this intuitive definition to define conditional probability formally. Then we will finish by covering some important properties of conditional probability. The prerequisites for this material are essentially the previous video on probability. You need to be familiar with the intuitive definition of probability and also with probability spaces. Let's get things started with an example. Imagine they have hired you, for example, at JFK Airport to model under what conditions flights are going to be late. And in particular, they're interested in finding out what is the probability that a flight is late if it's raining. Okay, so let's model this probabilistically. We build a probability space where we have two events of interest. L, which is that a flight is late, and R, which is that it's raining. And now remember that probability spaces have a sample space, a collection of events, and then a probability measure defined on the events. Here, we're not going to worry too much about the sample space of outcomes. We have already said that there are these two events of interest, and we're going to consider that we incorporate within the collection every possible union, intersection, and of course complements of these events of interest. So let me maybe use a Venn diagram to draw the sample space with the events. Okay, so this would be the sample space. And I'm going to draw our two events of interest. This will be, oops, sorry about that. This would be L, and this is going to be R. Let me annotate them. So this is R, and this is L. Okay, and I'm going to save this figure for later because it might come in handy. Okay, so remember that when we defined a probability measure on a probability space, a reasonable strategy is to assign probabilities to a small partition of events. By small, I mean a partition of small events that essentially cover everything we're interested in. So in this case, if you look at this picture that I drew, we probably want to assign probabilities to these small events like the intersection of R and L complement, the intersection of L and R complement, and so on. This will give us a partition that covers the whole sample space and includes the events that we're interested in. Okay, so that's essentially what we're going to do. Let me paste my picture here again, just to make it clear. So what we're doing is we're assigning probabilities to these small events. For example, the intersection between L and R is here. That has probability 3/20. The intersection of L and the complement of R, L and the complement of R, which is this, has probability 2/20. You might realize that the picture that I've drawn, is not really consistent with this, right? Because the area of these events should correspond to these probabilities, and they don't, because I drew the picture before showing you the numerical values. So what can you do? But that's so that you get a graphical idea of what we're talking about. Okay, so let's imagine that from past data, we have determined that these are the probabilities of these events of interest, and we're going to use them to try to answer this question. How likely is it that a flight is late if it rains? We don't know how to do this, but we can start by seeing what the probability is that a flight is late. Remember that the intuition here is that we're modeling our uncertain phenomenon of interest as a repeatable experiment that has mutually exclusive outcomes, and this experiment we can repeat it over and over and over and over And then we interpret the probability of an event as the fraction of times that the outcomes, when we repeat things over and over and over, that the outcomes are in that event. Okay, so in this case it would be, we repeat this flight arrival over and over and over, and we count how many times the airplane is late, and we divide by the number of experiments or the number of repetitions, and that would give us the probability of the airplane being late. It turns out that we have these probabilities down here, which I've copied from the previous slide, and from them we can actually compute the probability that the plane is late. We go back here, we see that the event late is just the union of this event here, which is L intersection R complement, and this event here, which is L intersection R. So these two events are disjoint. We can just add up their individual probabilities that, again, we assume that we have estimated from data. And we're going to talk, in fact, in the next video about how you would go about estimating probabilities from data. But for now, we're just assuming that these probabilities are given to us. So yeah, again, we have that L is the union of these two events that I just showed you. And now we can just add their probabilities. Okay, because they are disjoint. And it turns out that the probability of late with, based on these probabilities that we have estimated from data, the probability of late is 1/4. Okay, is this the probability we want? It is not, right? It's not the probability we want. We want to know the probability that the plane is late if it rains. Okay, so now I want you to think about how you would go about adapting this definition to capture that. How would you adapt it? Imagine that we still have this experiment that we can repeat over and over and over and over, and then we can take a look at the outcomes. How would you adapt this definition to compute the conditional probability that we are interested in, which is the conditional probability of late if it rains? Whenever I ask a question, I really encourage you to press pause and think a little bit about it. Okay, so we're saying that we're only interested in cases when it rains. We're only interested in the outcomes when it rains. So it doesn't make sense to consider all the total repetitions, right? We should only consider the number of times that it rains, right? We are interested in the number of times that the airplane is late, right? So another question, do you think we should keep the numerator as it is? Because we're interested in the times that it rains, we're changing the total repetitions to the repetitions only when we observe that it rains. Should we keep that numerator? The answer is no, because in that numerator, there's the times that the plane is late and it rains, and there's the times that the plane is late and it does not rain, right? So this fraction in particular, if we keep it like that, could be above 1. We're only interested in the instances when it rains. So we should replace this by saying the number of times that the airplane is late and it, wow, sorry for my handwriting, and it rains. Okay? And that's going to be our intuitive definition of conditional probability. We assume that the experiment can be repeated over and over and over. If we're conditioning on an event, we are only going to preserve the repetitions, the outcomes of the experiment that are within that event. And out of those, we see what is the fraction of our other event of interest. In this case, that the airplane is late. Okay, that's our intuitive definition of conditional probability. Let's see what are the implications of this intuitive definition. We can multiply and divide by the total repetitions, and like this, we actually obtain a formula in terms of probabilities that we already know, because the time the airplane is late and it rains divided by the total repetitions, that's essentially by definition the probability of late and rain, right, by the intuitive definition. And here, time it rains divided by total repetitions, this is just 1 over the probability of rain, by the intuitive definition that we already covered in the previous video. Okay, so an implication of our definition is that a reasonable definition for conditional probability is that it should be equal to the probability of the intersection of the two events of interest divided by the probability of the event that we are conditioning on. Let's apply it to our example. We actually have everything that we need, right? Because we have the probability of the intersection, and in order to compute the probability of R, we again divide, well, we express R as the union of R intersection L, so this guy again, and R intersection L complement. Okay, we add those guys up, and we obtain that, according to our new definition, the probability that a plane is late, given that it rains, is 3/4, which is 3 times bigger than the probability that the plane is late, and we don't know whether it rains or not. Okay, which, you know, in this case, I mean, of course, I've set the probabilities like that. It makes sense because airplanes tend to be late more often when it rains. Okay, so now we have developed an intuitive definition for conditional probability. Let's go back to the formal mathematical framework of probability spaces, and let's see what we have there. Okay, so remember that a probability space is formed by the sample space that includes all the possible outcomes, collection of events that, you know, technically has to be a sigma algebra, which is this scary sounding name for this, but basically it's just a collection of events that has to satisfy some reasonable conditions, and then a probability measure that assigns probabilities to the events. Okay, so now let's assume that we know, okay, someone tells us, or we see from the data or whatever, that an event A has happened, which means that all the outcomes that we want to consider are now restricted to B in A. But that is all we know. So now the question is, how do we adapt this probability space in order to incorporate this new information? And by the way, I mean, I should have said this earlier probably, but the whole point of conditional probability is to incorporate additional information. So we have a probability space that characterizes the uncertainty associated to a certain phenomenon, but now suddenly we have we get an additional piece of information, for example, that it's raining, let's say, in the case where we are interested in whether flights are late. And now the question is, how do you incorporate that new information? And this is exactly what we're doing here. And here in particular, we're making this formal mathematically. Okay, so how do we adapt the probability space to this additional information that the outcome is going to be in the event A? We have to adapt 3 things, right? The sample space, the collection of events, and the probability measure. Okay, so I want you to think about this, as we go along. So what should be the new sample space? And again, I encourage you to just pause the video and think about it. The new sample space, if you think about it, all the outcomes that we're going to be interested in are going to be in A. So the new sample space should probably be A. Okay? Maybe let me go back to the picture just for a moment. When we were talking about the airplane being late when it rains, we're conditioning on it raining, right? So what essentially we were saying is that we just wanted to consider the outcomes in R and none of the other outcomes, right? Like the other outcomes, we don't care about them. We throw them to the trash and we keep this circle of outcomes. So it's logical to just say, okay, now our new sample space is going to be this circle. That's it. Okay, does that make sense? So now, what should be the new collection of events? Because we're only considering outcomes that are in A, if we have a new event B, not a new event, but an event V, in this case L, okay, like we're interested in L here, and we're interested in L, now we know that the outcomes that we're going to consider that are in L are also going to be in R. Okay. In our case, if we're conditioning on A, those outcomes are also going to be on A. So maybe I'll finish with this example to not confuse you, and then we'll move on. So what I'm saying is here, if we're interested in here, if we're interested in L, instead of considering L this, now that we know that our outcomes of interest are going to be also in R, it makes sense to represent L under this new information with the intersection between L and R. Okay, maybe I should have said, yeah. It would make sense to just consider L the intersection between L and R. Okay, so to not confuse you further, goodbye previous example. And now let's continue here. So, okay, so we've said the new sample space, if we condition on an event A, should be that event A. What should be the collection of events? If we have another event B that we're interested in, we don't want to consider B, we rather want to consider B intersection A, because all of the outcomes are also going to be in A. So we can replace every event B in the original collection by the event intersection between A and B. Okay, now what should be the probability measure? How should we update the probability measure? Well, we're considering, like we're representing each event by its intersection with A. So maybe we should just say, well, it's the probability of the intersection. Do you think this would yield a valid probability measure? To see, to see whether this is the case, we can compute the probability of the whole new sample space. The whole new sample space is A. The probability of A under this definition would be the probability of A intersection A, which is the probability of A, which is equal to not necessarily 1, right? It's whatever the original probability measure assigned to A. So now we have gotten a new probability space where the whole sample space does not have probability 1. That doesn't really work very well. But it has a simple solution. We can just normalize and divide by the probability of A, all of the probability measure. And this actually yields exactly the same definition that we had arrived to with our intuitive definition. We have that the conditional probability of B given A is just the probability of the intersection divided by the probability of A, which completely coincides with our intuitive definition, which is pretty cool. When we're doing probabilistic modeling, often we refer to probability of B as a prior probability, because that's before you have this additional information, and probability of B given A as a posterior probability, because this is the update of the probability of of B. This is the probability of B given A. That's called a posterior because it's how we have updated the probability after we have gained this additional information. This is used a lot in Bayesian statistics. We'll talk much more about that later on. Okay, so now I want to show you kind of a picture that is kind of similar to the picture that I showed you before with latent rain, but it's a bit prettier. So this is the original. Here on the left, we have the original probability, the original sample space, and I've shaded the probability of A intersection B. And now the idea is that we're conditioning on A. So now we're only going to be interested in this square here, and we discard everything else, right? Like exactly as I had said. But now that square has area smaller than 1, right? Whatever probability, the probability measure assigned to it. So we have to blow it up so that it has probability 1, and it's a valid, and the probability measure is a valid probability measure. Now, if we're interested in this other set B, because we know that all outcomes are going to be in A, we only pick this part of B, okay, which is there. And when we blow it up, that part goes from having probability A intersection B to probability A intersection B divided by probability of A, because we have blown up everything by probability of A. Okay, that's a visual representation of how we have adapted this probability space to assume that A has happened. Just a note about notation. When we write intersections between many events, it gets a bit cumbersome, so sometimes we just write commas. And when conditioning on intersections between a lot of events, we also often write commas. Okay, so we have already provided an intuitive definition of conditional probability and a formal definition of conditional probability. Now we're going to see some implications of this definition that are really important for probabilistic modeling. The first one is the chain rule. The chain rule just follows, it's an immediate consequence of the definition. So we have just seen that the probability of B given A is the probability of the intersection divided by the probability of A, right? So now we move this here, and boom, we have the chain rule, okay, which is this. It also works the other way around. You can consider the probability of A given B, and you get this other formula. When you have 3 events, you can do this kind of in 2 steps. First, you consider the event B intersection C, like to make it maybe a little bit easier, you can call that the event D. And then you have that the probability of A intersection D is the probability of A times the probability of D conditioned on A, just by the chain rule between 2 events. But now we can further expand this, because we can just apply the chain rule to the probability measure that conditions on A. Okay, we can apply the chain rule to that probability measure. That's a kind of a quick explanation, but let me give you a little bit of a more detailed explanation, which also will help us to review some of these concepts. So here we want to expand this guy. Let's consider the probability of C given A and B. Okay, that's the probability of A intersection B intersection C divided by the probability of A intersection B. But now we can apply the chain rule up and down, and we can get that this is just equal to the probability of B intersection C conditioned on A times probability of A divided by the probability of B intersection A probability of A. And now we can cancel out these probabilities of A, and we get an expression for the probability of B intersection C conditioned on A, which is the probability of C conditioned on the intersection times the probability of B conditioned on A. Okay, so this times this, we can plug in here. And what we obtain is the chain rule for 3 events. And I like to think of it in these terms. Okay, so I have 3 events. I take one out. By take one out, I mean I write the probability of A. Now I've taken A out, so I have to condition everything else that I take out on A. Okay, so now I take out B. So I have the probability of B given A because I've taken out previously. And now I need to take out the last one, which is C, and I have to condition on everything that I've taken out before, the intersection of everything that I've taken out before. Okay, hopefully this helps you. I can do this in any order I want. I could have taken out first C, then B, then A, for example. Okay, the order is completely arbitrary. And this, by exactly the same argument, extends to any number of events. So let's say that we call the events S1, S2, S3, up to whatever you want. The idea is that if we have the probability of the intersection between all of these events, we can express it as this chain of conditional probabilities where we take one out, probability of that one, probability of another one given that guy, probability of a new one given what the intersection between everything that we have taken out, and so on and so on and so on. Okay, and that's the chain rule. It's very important to remember that this order is arbitrary. The reason why it's important is that in probabilistic modeling and also homeworks, choosing the order wisely is going to be very important. Okay, so that was the chain rule. Another very important property of conditional probabilities is the law of total probability. Okay, so the law of total probability applies when we have a partition. So this is our sample space, and we have a partition of A1, A2, and A3 in this case that these are disjoint events that cover our sample space. Now we're interested in the probability of another event S, the probability of another event S, and we only have access to the probability of S conditioned on each of these guys. Okay, we'll see an example in a moment, but this actually happens relatively often in practice. You have access to some conditional probabilities and you want to aggregate them to get the probability of an event of interest. Okay, so how do you do it? Well, you divide this guy into these pieces that belong to the different elements of the partition, and then basically you add them up. I mean, these are disjoint events. The union of them make up your event of interest S. You can just add them up to get the probability of S. And now if you have access to the conditional probabilities, then you express each of these guys in terms of the chain rule. So this one in particular would be P of A1, P of S given A1. Okay? And that is the law of total probability. Let's define it a little bit more formally. Remember that a partition of events of the sample space is just a collection of events that are all disjoint, and if you take their union, they cover the whole sample space. Now we want to express the probability of S in terms of those events. Well, as we just saw, the union of the intersections of S with each of the individual events is going to give you S, and you can add up those probabilities to obtain the probability of S just by these basic properties of probability measures. And now we can just split that using the chain rule. Okay, and this is what is called the law of total probability. To be honest, I often don't apply it directly. I just rederive it because I think that that's kind of more intuitive, and like that you don't have to memorize formulas, but here is the formula. Let's take a look at an example. Imagine that you have this data, and from the data you have determined these conditional probabilities. Okay, and now you find out that the probability that it rains tomorrow is 0.2. Okay, I mean actually it's the fall in New York City. Maybe 0.2 is not a bad estimate for the probability. So you want to use these conditional probabilities. You need to aggregate them to compute the probability that a flight, maybe your aunt is coming to visit tomorrow or something, that her flight is late. So what do? You apply the law of total probability. But again, I usually just like to rederive it. So the probability of late is just the union between late intersection rain and late intersection no rain. Okay, and you can add them up because they're disjoint events. And now these guys, you just apply the chain rule. Okay, so this guy is the intersection between R and L is just probability of R times the probability of L given R. And again, the chain rule is just a direct implication of the definition of conditional probability. And we do the same for the intersection between R complement and L. And now we just plug in the numbers and we get that there's 1/4. The probability is 1/4. Okay, that your aunt, the flight your aunt is taking will be late. Okay, so again, the law of total probability allows us to aggregate conditional probabilities to compute the probability of an event that we're interested in. Okay, so now let's take a closer look at conditional probabilities because the first time you start dealing with them, you might be tempted to say, well, isn't the probability of A given B essentially the same as the probability of B given A? And it's really not. And let me give you an example. So consider that A is playing in the NBA and B is owning a basketball. So what's the probability of owning a basketball if you play in the NBA? Okay, so probability of B given A. It's really high. I think, given that they probably own mansions and private islands or whatever, they probably own a basketball. What's the probability that you play in the NBA if you own a basketball? Well, I own a basketball. It's really, really, really low. So why does this happen? Because, the definition for both of them is quite similar. So the reason why it happens is that both are equal to the probability of the intersection between A and B, but they're normalized by different amounts. They're normalized by either probability of B or probability of A. the probability of owning a basketball is much, much higher than the probability of playing in the NBA. So as a result, the conditional probability is much, much lower. Okay, so that makes sense. Let me show you with a picture. So here is like an original, here's an original sample space, which has these two events, A and B. Okay, and here B would be maybe playing in the NBA, and A would be owning a basketball because B is smaller. So when we condition on A, we blow up A, but here we're not blowing it up by that much. So the conditional probability is not blown up by that much because A was already quite big. Here, when we condition on playing in the NBA, it blows it up a lot. Okay, so the probability of owning a basketball given playing in the NBA is blown up by a lot because what matters is how much, what fraction of the event of interest is taken up by the intersection. Okay, and the intersection takes up a large fraction of B. It does not take a large fraction of A. Okay, so hopefully this visual representation allows you to understand the asymmetry between the two conditional probabilities better. Okay, so you actually can invert conditional probabilities because, as we have seen, they're super related, but you have to be careful to reweight by the appropriate amounts. So we already saw that, the probability of, but actually we already saw, like the chain rule essentially tells you that probability of A given B by times probability of B is the probability of the intersection, and this is the same, exactly the same as the probability of B given A times the probability of A. Okay, this is the chain rule. So now you can just, divide by probability of B on both sides, and you get what's called Bayes' rule, which tells you how to invert conditional probabilities. And here, invert is a little bit, in air quotes, because we're not really inverting, we're just reweighting the conditional probability by essentially recomputing the probability of the intersection and then dividing it by the appropriate probability. But yeah, that's Bayes' rule. Okay. Again, I usually tend to like to rederive Bayes' rule as I'm computing stuff, but here you have the formula. And as you can see, it's direct consequence of the previous definitions. Okay, so let's go back to flights and rain. Imagine that, again, in this situation before, we know the conditional probabilities of the flight being late given rain and no rain. And now we hear that a flight was late, and we don't know whether it rained or not that day. So now we want to, you think, so then how likely is it that it rained, given that the flight was late? We have to invert these probabilities, but we have to do it carefully. So let's do it. Again, I usually like to go through the definition. So by definition, the conditional probability of R given L is just the probability of the intersection divided by the probability of late. Okay? And now we're going to expand this guy so that we can use the information that we have. Okay, and the information that we have is late given R and R. So we're going to expand the chain rule in that direction. And this guy here, we're going to express it as a union of events, and then we're going to do the same for those events. Okay, so here we have applied the chain rule. Here we have expressed the probability of late in terms of, as a union of the late and R and late and not R, as we had done previously. And now these guys, okay, here in the bottom, we can again apply the chain rule. And now we have all the probabilities that we need. By the way, when I'm going through these examples, I again encourage you, stop at the beginning, try to do them quickly on a piece of paper, and then you can check. And maybe I'm wrong, and you have to tell me. I have been wrong before. So, okay, you plug in the numbers, and the probability that it was raining if you find out that a plane is late is 0.6. Okay, which makes sense, right? The probability of rain is 0.2, but if you know that a plane is late, since planes are late because of rain, it makes sense that it increases. To know how much it increases, you have to apply Bayes' rule. Okay, you have to reweight appropriately. Okay, so that was essentially it. What have we learned? We have covered an intuitive and then a formal definition of conditional probability, which is a very important object that allows us to update our probabilistic models with additional information. And then we have covered important properties of conditional probability, such as the chain rule, the law of total probability, and Bayes' rule. Thank you very much.